Pyrex dielectrical barrier in contact with the discharge, and we have seen no excess energy. So that's a blank experiment, which could be an answer to your remark, which is in fact that if you look to the Pyrex, you are more or less in the levels of high value chemical or physical reaction of modification of the Pyrex. What is expected? The discussion I had with people which are knowledgeable in dielectrics, in fact, was that dielectrics can have modifications of their state, yielding phase transitions with energy in the range of maybe 1 kilocal per mole of Pyrex. And this has been shown not to be the case by blank experiments. That's the answer. So, the conclusion is that a reaction is occurring with high energy release per atom hydrogen, and second, hydrogen is lost in an unexplainable way because we have found no leakage and no combination with materials in the reactor which could explain the results.
Can you weigh the palladium after the experiment?
Yeah, and in fact what we found, yeah, right, we did it. Of course this can be slightly discussed, because to weigh it you have to take it out from the reactor, and then you can argue that you are losing part of the hydrogen when weighing. The experiment, what we have observed very consistently is that when loading when loading palladium to ratio 1, and when exposing it later to the atmosphere, you have a very fast, I would say a few tens of minutes at room temperature, a very fast loss of hydrogen until 0.7 loading ratio. That is, what is loaded above the usual loading ratio is going out from the metal very fast, but the rest you take several days to take out the hydrogen. So what I measure after the experiment, I measure the remaining of the hydrogen between 1 and 0.7. I'm losing what is between 1 and 0.7, which is a very small amount, which cannot explain the whole consumption, and I'm checking that there is no excess hydrogen in the electrode itself, which could be occluded in defects or in things where, because one of the objections I had was the following. If you take a piece of palladium and then you load it, if you have defects inside which are strong enough and the metal is strong enough to withstand the pressure, you can push hydrogen in these defects in the form of molecular hydrogen at a very high pressure, and this you will not see it unless you weigh it. And the idea of weighing it was to answer the objection: you have hydrogen occluded in the palladium, which you don't see if you don't weigh it. So I weighed it, and I found back 0.7 as a loading ratio. Okay. So the only thing which you can say we are losing hydrogen is between 1 and 0.7 loading ratio, which cannot explain 5.5 to 0.7. Okay, so I think I will answer your objection. Yeah?
Did you try and monitor helium during these experiments?
No. For the time being, we have not measured any, we have not tried to measure any helium in these experiments, because the first objective was to check that the excess energy measured in the first period experiment could be reproduced with a completely different system, which is the case because we reproduce it. And for the time being, so we are practically sure of the excess energy, and now we are going to make some helium measurements, but we have made neutron measurements, and we have found nothing. It was still in the background. That's 2 months. So we are faced with a problem. The conclusion for the time being is that we are really sure that there is an excess energy production, and because we have used two completely different setups, and we find an excess energy production. We find an excess energy production with hydrogen, which is in the order of 1,000 of electron volts per atom. We have in mind an explanation, which is for the time being still highly hypothetical. This explanation has already been put forward by various authors, which is the formation of a tightly bound state between an atom of hydrogen and an electron inside the palladium. That is, instead of having a combination between a bond state between a proton and an electron with an energy of 13 eV, then you have to think to a bond state with a proton and an electron much closer to the proton, which can, of course, when you form this bond state, you have an excess energy of 6,000 eV. But that, of course, is highly hypothetical, because when you discuss that with people, they say it's even more difficult to swallow that confusion, because, of course, this is real known physics. Well, it's known physics in vacuum, of course, because when you are writing the equation of a proton and an electron, you are in vacuum. You have not the influence of the rest of the lattice of the palladium. So one idea we have in mind is to say, in this experiment, and we are for the time being running deuterium experiments, and to see if we have the same behavior with deuterium. So for the time being, we say, as an hypothesis, as a working hypothesis, we are forming a tightly bound state between hydrogen or deuterium and an electron in the palladium, which really is a high amount of energy per atom hydrogen, something in between the chemical range and the nuclear range. And of course, if you start thinking of the behavior of this type of bond state, they should be small, of course. The dimension of for 13 eV energy is something like 1 angstrom, and that's the radius, roughly the radius of the hydrogen atom. If it's more tight, then you have dimension of the order of 200, 300 femtometer, and that's very, very small. And you might explain a number of weak nuclear signature by allowed nuclear reaction in the metal between, for instance, the nuclear of Palladius and of Palladium and the electron of this bound state. But this is only a hypothesis. You can have electron capture, and you can explain transmutation. Well, you can explain a number of things by taking into account the hypothesis of atom of hydrogen with the electron closer to the proton than in normal state. Well, we are starting this setting with theoreticians to see whether this idea is crazy or not, and we are in fact testing the consequences of this hypothesis. But for the time being, we have no evidence. So the overall conclusion is that we have measured an excess energy. We have confirmed an excess energy in the system hydrogen palladium. We have seen that if we are producing ashes, then the level, the nuclear ashes, the level observed is much too low to explain the excess energy production observed. And we are now orienting our research in a slightly different direction, taking into account this hypothesis. Thank you.
Are there any questions?
What is the relationship of what might be going on in the system to the aqueous system in which deuterium gives you excess energy but hydrogen doesn't? Is this related at all? I'm completely lost on that.
Sorry, could you repeat that?
Okay, I don't work in this field,
Yeah?
so I'm asking very naive questions. In the aqueous system,
Yeah.
first publicized by
right.
Planck, deuterium D2O gave you excess energy, but hydrogen H2O did not.
Uh-huh.
And in this system, you get excess energy with hydrogen, and you say with deuterium as well?
Yeah, but I have to check that because I have less experiments with deuterium.
Okay. Is there any relationship between these gas phase experiments and the
okay, that's a very good
experiments
question.
in which hydrogen gives
Okay.
no result?
I think that, well, I think that you need first to have hydrogen in the metal. And you have a number of ways to do that. You can do that by electrolysis, of course. You can do that by pressure loading. You can do that by arcing or by discharge at low pressure. You can do that by discharge at high pressure. Why is it so? Because when you use atmospheric pressure to load deuterium, the thermodynamics says that you will get 0.7 atom hydrogen per atom palladium. And using electrolysis or using gas discharge or using high pressure or any kind of thing is just to shift this thermodynamic equilibrium, and then you can increase the amount of hydrogen in the metal. So all experiments have in common, whatever is the way you use, is to increase the hydrogen content of the palladium. So that's one common point. Okay. There might be differences in the micro state of the palladium depending on the various way of loading. I mean, if for instance you are using a low pressure gas discharge, then you are speaking of the so-called Thomson mechanism, and you have a discharge which is completely evenly spreaded on your electrode. So the electrode sees an average current which is low, which is the dividing the total current by the electrode surface. Okay. If you are, for instance, using a high pressure discharge, which is what I do, then the mechanism is completely different, and you are using what's so-called streamer mechanism. That is, the discharge is the accumulation of very small sparks impacting the metal, which means that at each impact the metal sees a very high current, even if the average current is the same for all the experiments. So you can have within the metal difference of conditions between, you see what happens in all experiments using electrolysis or gas discharge is that you have a current flowing through an hydrogen loaded metal. So in the case of electrolysis, I know I had some discussion, for instance, with Celani, who is working on that field in Italy, and he says that he has better results, but he is electrolyzing the system, so it's heavy water electrolysis. But instead of delivering an even current, he delivers pulses of very high intensity, and just to try to be in the same situation, for instance, as we have here in the discharge. And then it's slightly different. So to completely answer your question, I said that the common thing in all these experiments is to try to go at a higher loading ratio than usual. And then you may have differences in the way that the current is flowing in the electrode, and I think this is very important. The way the current is flowing through the electrode is extremely important, because you create probably some non-equilibrium situation. You have a flow of proton one direction, flow of electron in another, etc. And I think that it is under these circumstances that you may have a reorganization of the binding between them. That's purely hypothetical.
But it is true, we don't normally see it succeed in light water.
Yeah, right.
Electrolysis, but we do in heavy water. And that's because of this, right?
Maybe I have another answer, because I think apparently there are, when you are working on heavy water, you do much less experiments when you are working on light water. In my case, I always find excess energy with deuterium, and I've been doing lots of experiments on hydrogen, and the result is that, of course, some gives no results as all experiments, but a number give very positive results. And the second answer is that there is a number of experiments which have been run with nickel and light water, which apparently give an excess energy also.
Electrolysis.
Yeah. So I think that's at least more general. That's why we decided to study the system deuterium hydrogen. And apparently the system deuterium hydrogen gives level.
There's a new school developing a cofusion of electrolysis that claim excess heat in like water with nickel. That Randy Mills was the beginning of that.
The interesting thing is your explanation, one the hypothesis is that you could have this tightly bound state of an electron.
Yeah, so it could happen either with...
That is Randy Mills' explanation.
Yeah, right.
But he said it was a 1/2 quantum measure. That would give you
This is not what I have in mind, because this is not acceptable. I just say I don't know exactly what's happening in the metal, and honestly, difficult to, for the time being, put forward a correct, at least qualitative mechanism. What might happen? There are strange things in the system hydrogen palladium, by the way, or hydride forming metal in general, is that when you apply an electrical field, you have a rate of migration velocity of the hydrogen, which is several orders of magnitude higher than with helium or with any atom with more than one electron. So probably the hydrogen and its isotopes have a very special behavior in palladium. And this is probably related to that. I'm convinced of that. This is a hypothesis.
So, but it is for sure ruled out that it is not a nuclear mechanism.
Well, to answer your question, I think the basis of the thing is not nuclear, but at least when you accept this explanation, you can explain why you can have a number of nuclear manifestations behind, like transmutation or even protection of tritium, etc. But I think it is not the basic phenomenon. And I think it was probably, well, that's my opinion, I think it was a strategical error at the beginning to claim that it was cold fusion. That's only my opinion. Because I think there is really something very interesting, but it has been, more or less devaluated by saying it. But I may be wrong. That's purely my opinion.
There are results coming out where they think that the deuterium or hydrogen atom does invade the plate nucleus, and that would maybe relate to your theory.
That could be, well, just by the electron. I don't believe in the overcoming of the Coulomb barrier, especially when you take a big nucleus, of course. But you can bring, at the proximity of the nucleus, if you bring this bound state, then you can capture its electron.
They find some evidence for transmutation.
Yeah, there are evidence of transmutation which can be easily explained by this mechanism, but with not violating any. So the very, very great difficulty is to accept, of course, the formation of this bound state. That's difficult to explain for the time. So what you are doing? Yeah.
You measured ash for chemical byproducts, I take it, from this reaction. Did you consider volatiles as being a chemical byproduct in the outgas stream?
Chemical byproducts, yeah. And we didn't see any special chemical byproducts.
So you would have measured for things like water in the outgassing?
In fact, you see, I introduced some water in my reactor to see the behavior, and you see at once it deposits on the wall, and the quantities you couldn't see as being deposited on the walls are so low that they cannot explain by a factor of 1 million the excess energy. So we did all that, of course.
You mentioned that the first few years that you worked on this, you were working on your own at Shell in your spare time.
Yeah.
And then over the past couple or 3 years, you've been working elsewhere with Shell support. Is that going to continue? Is that
that's a key issue.
Is Shell still interested in
in fact, I can give you a complete answer. Shell is interested in the phenomenon because we have already taken 2 patents on this system which we are maintaining. Okay, that's the first question, the first answer. Second answer: why is Shell going on funding this system, or at least until the end of '95? I'm sure of my funding until the end of '95. Afterward, I don't know. First, because they don't want to appear. Well, I had a number of discussions with Shell research people in The Hague, and they wouldn't like to appear as people blocking development of new energy. Of course, if it is interesting, we are interested in doing something. The main problem I have, and you might have the same problem here, that you know that all organizations are reducing their research costs, I can call them costs, and second, concentrating on their core business. So the impression which is dominating for the time being in Shell is, okay, that's interesting, but that's not our core business. So Mr. Dufour, if you can try to find another sponsor who would be more interested, then we could do something together. But so my feeling is that they are not willing to go on funding, at least by themselves, only Shell after 95. In fact, what I'm doing actually is I'm trying to find some other company interested in co-founding the work.
I guess it's time for lunch. Let's thank Dr. Dufour again.